Hello friends. So today we are going to discuss questions from the year 2022, and there are total of 19 questions, and the questions are from the mains as well as advanced. And this is part 1 from the year 2022. So first question, and it states that sodium light of wavelength 650 nanometer and 655 nanometer is used to study diffraction at a single slit of aperture 0.5 millimeter. The distance between the slit and the screen is 2 meter. The separation between the position of the first maxima of the diffraction pattern obtained in two cases is. So we have to find out, because we have two wavelengths, and because of that we are going to get the two maximas, and it says that for two wavelengths what will be the separation between the first maximas. Okay. So we are given two wavelengths. First of all, first wavelength is of lambda 1, that is over 650 nanometer, 10 raised to power minus 9 meters, and we have second wavelength, that is 655 nanometer, and slit width, that is of A, that is given as 0.5 millimeter, and that can be 10 raised to power minus 3 meters, and the distance between the screen is, let us suppose, that is given as capital L, and that is our 2 meters. And for this calculation we are going to use two formulas, and the first formula is that for the first maxima in a single slit diffraction, that is A sine of theta is equal to 3/2 lambda, and also we are going to use small angle approximation, that sine of theta is equal to tangent of theta, which is equal to y upon L. We are going to use two formulas. First maxima in single slit diffraction, and that is our A sine of theta is equal to 3/2 times lambda, and second one we are going to use small angles, so which basically means that sine of theta can be approximately equal to tangent of theta, and that will be equal to y upon L, and here y is the position on the screen. So we have two wavelengths, so accordingly we can modify the formula, and you can say that for lambda 1 we can write this as A sine of theta 1 is equal to 3/2 lambda 1, and for the small angle we can write sine of theta 1 is equal to approximately equal to tangent of theta 1, and we can write that will be equal to y1 upon L. Therefore we can write that A times y upon L is equal to 3/2 times lambda 1, and from here we can write the formula for y1, which will be equal to 3 lambda 1 L upon 2 multiplied by A, and we know all the values for it. So we substitute it, we get y1 will be equal to 3 lambda 1 is of 650 into 10 to the power minus 9, and L is 2 meters. This becomes 0.5 into 10 to the power minus 3 meters. So from here we get that y will be approximately equal to 3.9 into 10 to the power minus 3 meters. Similarly, we solve for lambda 2. You can say for lambda 2, once again we can write it as y2 will be equal to 3 times lambda 2 L multiplied by 2A. We substitute the values, we get y2 will be equal to 655 into 10 to the power minus 9. Length is given as 2, and this becomes 2 multiplied by A, that is 0.5 into 10 to the power minus 3. This gives us that y2 will be equal to 3.93 into 10 to the power minus 3 meters. And we need to find out the difference. Therefore, we can say that our delta y is y2 minus y1. y2 is our 3.93 minus 3.9 into 10 to the power minus 3, and this comes as 0.03 into 10 to the power minus 3 meters. Okay. Or we can further write it that delta y is equal to 3 into 10 to the power minus 5 meters. Therefore, it is 3. Next question. We are given that two light beams having intensities I and 9I interferes to produce a fringe pattern on the screen. The phase difference between the beams is pi by 2 at P and pi at Q. Then the difference between the resultant intensity at P and Q will be. So we are given two intensities. Let us call them beam 1 having intensity of I1, and that is equal to I, and then we have beam 2, let us call this I2, having intensity of 9i rather, and we are also given the phase difference. So you can say the phase difference at P, let us call that as phi of P is equal to pi by 2, and we have phase difference at Q, let us call that as phi of Q, that is equal to pi. In this case, we are going to use the formula that the resultant intensity is equal to I1 plus I2 twice square root of I1 I2 and cos of the phase difference. Okay. So we have 2 points, so therefore we can modify the formula that we can say for point P, you can say this I of P is equal to I1 plus I2 twice square root of I1 I2 and we have cos of phi p. So we get here ip is equal to I plus 9i twice of I multiplied by 9i, and we have cos of pi by 2. Cos of pi by 2 is 0, so therefore this entire terms goes away, and we get this ip is equal to 10i. Similarly, we can write for our iq. You can say for point q, our iq will be equal to I plus 9i plus square root twice I multiplied by 9i and cos of pi. So we get here iq will be equal to 10i, and cos of pi is our minus 1. So this goes minus, and this comes as 3 to 6 pi. So this gives us that our iq is equal to 4 times I. So we found out IP as well as IQ, and we have to find out the difference between IP and IQ. So we can say delta I is our IP minus IQ, that is 10I minus 4I, giving us 6I. So option number B is the correct one. Option B is correct. Next question, and it states that the interference pattern is obtained with two coherent light sources of intensity ratio 4:1 and ratio I max plus I mean. I max minus I mean is 5 by x. Then the value of x will be equal to. So here we are given that ratio of I max plus I mean and I max minus I mean is equal to 5 by x. And we are given that the intensity ratio of two coherent sources is 4:1. So if the intensities are I1 and I2, so let us assume that intensities are I1 and I2. Therefore, we can write that our I max will be equal to square root of I1 plus square root of I2 whole square, and our I mean will be equal to square root of I1 minus square root of I2, and this is whole square, and the ratio is given as you can say 4:1. Therefore, we can write that you can say let I1 is equal to 4k and our I2 is equal to coming as k. We can find out our I max will be equal to 4k square root plus k square root and whole square, and this will be coming as 2 root k and 3 root k whole square and giving us 9k. Similarly, we can find out our I mean, that will be square root of 4k minus square root of k whole square, and this will be coming as square root of k whole square and coming as k. And we can substitute it in this equation. Let us call this as equation number 1. So you can say from equation 1, we have I max plus I mean, that is 9k plus k, and 9k minus k is equal to 5 upon k, 5 upon x, that is given to us. So we can write this will be coming as 10k upon 8k is equal to 5 upon x, and here k and k goes away, and this goes by 4 and this goes by 5. So this gives us that our 5 upon x is equal to 5 upon 4, giving us that our x is equal to 4. So option number B is the correct option. Option B is correct. Next question. We are given that in free space an EM wave of 3 GHz frequency strikes over the edge of an object of size lambda by 100, where lambda is the wavelength of the wave in free space. The phenomena which happens there will be. So we have to find out which of these phenomena is going to take place. And we can say that for each of these phenomena to take place, there is a relationship between the obstacle as well as the wavelength. Okay. So first is our for reflection. For reflection, the size of obstacle must be much larger than the wavelength. You can say that size of obstacle must be much larger than the wavelength. Okay. And for diffraction, the size of the obstacle size should be the order of the wavelength. Order of wavelength. And the size that is given to us, that is lambda upon 100, and this is very much less than the wavelength. So only phenomena that is possible will be our scattering. So option number D is the correct one. Next question. We are given that for a specific wavelength 670 nanometer of light coming from a galaxy moving with velocity v, the observed wavelength is 670.7 nanometer. The value of v is. So it is basically, you can say, have a relationship between the Doppler effect. Okay. And in this case, we have a emitted wavelength that is lambda naught is equal to 670 nanometer, and then we have observed wavelength, that is our lambda is equal to 670.7 nanometer. Okay. And we are given that, or we can say we can use the Doppler effect, and that Doppler effect states that Doppler effect and which gives us that there is observed lambda is equal to our lambda naught square root of 1 plus V upon C divided by 1 minus V upon C. Okay. And for V, which is very much less than C, we can approximate the formula that our lambda will be equal to lambda naught, and this becomes 1 plus V upon C. And we can just solve it further, that from here we can write that lambda upon lambda naught is equal to 1 plus V upon C. This gives us that V upon C is equal to lambda upon lambda naught minus 1, giving us lambda minus lambda naught divided by lambda naught. And we have our V is equal to C times lambda minus lambda naught divided by lambda naught. And we know all these values. So we substitute it. We have velocity of light 3 into 10 to the power 8. Lambda was our 670.7 minus 670 and divided by 670. And this gives us that our velocity V will be approximately equal to 3.13 into 10 to the power 5 meter per second. So we have the 3.135. So option number C is the correct option. C is correct. Next question, and it states that in Young's double slit experiment, the two slits are 0.6 millimeter distance apart. Interference pattern is observed on screen at a distance 80 centimeter from the slits. The first dark fringe is observed on the screen directly opposite to one of the slit. The wavelength of the light will be in nanometer. So here the first dark fringe is directly opposite to one of the slit. So first of all, let's write what are the information given to us. So we are given that the distance between the slits, that is our small d, it is given as 0.6 millimeter. We can write 0.6 into 10 to the power minus 3 meter, and capital D is also given to us, that is our 80 centimeter. So we can write this as 0.8 meters. And the important part is there that first dark fringe is observed directly opposite to one of the slit. First dark fringe is directly opposite to one of slits. And for dark fringe, we already know the path difference formula. You can say for dark fringe, path difference that is given as n plus 1 by 2 times lambda, and here n is equal to 0, 1, 2 and so on. Therefore, the nth position of the fringe, nth dark fringe position, that is y of n, will be equal to n plus 1 by 2 lambda capital D divided by small d. And for first dark fringe, we can say value of n is equal to 0. You can say for first dark fringe n equal to 0. Therefore, we can write that y of 0 will be equal to lambda capital D divided by 2 small d. Okay. And it is also given that the first dark fringe is observed directly opposite to the one of the slits. So we are also given that first dark fringe is opposite to slit. So we can write that our y naught will be equal to capital D divided by small d divided by 2. So let us call this equation number 1 and this as equation number 2. So they are representing same thing. Therefore, we can equate equation 1 and 2. So you can say from equation 1 and 2, equation 1 and 2, we get small d by 2 is equal to lambda d divided by small d. And small 2d. Here 2 and 2 goes away. So we get our d square, or we need to find out lambda. So you can say lambda is equal to d square upon capital D. We substitute the value. This is 0.6 into 10 to the power minus 3 whole square, and we get this as capital D is given to us as 0.8. So this comes as 0.45 into 10 to the power minus 6 meters. Oh, it is asking nanometers. So we can write that our wavelength will be equal to 450 nanometers. So its answer is 450. Next question. And it states that in Young's double slit experiment performed using a monochromatic light of wavelength lambda, when a glass plate refractive index mu 1.5 of thickness x times lambda is introduced in the path of one of the interfering beams, the intensity at the position where the central maxima occurred previously remains unchanged. The value of x will be. So it means the position of central maxima before and after insertion of the glass plate is same. It does not change. So first of all, let's write the things which are given to us. We are given that we have a wavelength which is our lambda, and we have a refractive index of the glass plate, that is given to us as mu 1.5, and we have thickness of plate which is x times lambda, and the important part is that the intensity is not going to change. You can say intensity at previous central maxima remains unchanged. Intensity at previous central maxima remains unchanged. So it means that the path difference that is being introduced by the glass must be an integer multiple of the wavelength. We can say that the path difference should be the integer multiple of path difference should be integer multiple of wavelength, that we can say is n times lambda. And also, because of the insertion of the glass plate, the path difference is given by mu minus 1 multiplied by t. So we also say that path difference due to glass plate, that is given as mu minus 1 multiplied by t. And these two path difference, equation number 1 and equation number 2, are the representation of path difference for the respective. One is in terms of the multiple wavelength and another one in terms of the glass plate. So you can say that from equation 1 and 2, n times lambda should be equal to mu minus 1 multiplied by t, where t is the thickness. So we get this is n times lambda is equal to mu is given to us as 1.5 minus 1, and this is given to us as n times lambda, sorry, x times lambda. So here lambda and lambda goes away, so we get this as that our 0.5x should be equal to n, or we can write that our x should be equal to 2 times n, and the option number for the integral, so it will be integral multiple of n, so n will be 1, 2, 3, 4 and 5. So from here we can easily see that option number B is the correct one. You can say that x is equal to 2, so therefore option B is correct. B is correct because n will be an integral multiple, so it will be all integral multiple. So either it will be 2 or then it will be our, if value of n is 2 then it comes as 4, likewise it is coming 4, 6 and something like that. Next question, and it states that in Young's double slit experiment an angular width of fringe is 0.35 degree on the screen placed 2 meter away for a particular wavelength of 450 nanometer. The angular width of the fringe when whole system is immersed in a medium of refractive index 7/5 is 1 upon alpha. The value of alpha is. So here we have two fringe width. One is, you can say, in the air, and another one is in the liquid or medium for the refractive index of 7.5, and the angular width in that immersed medium is given as 1 upon alpha. So the information that is given to us, we can say that initial angular width let us suppose that is given as theta, which is our 0.35, and refractive index of the medium let us suppose that is given as mu is our 7.5, and we are also given the final angular width let us suppose that is given theta prime, that is equal to 1 upon alpha. And we know that the angular width is inversely proportional to the refractive index. We know that angular width is inversely proportional to refractive index. So therefore we can write that our theta prime will be equal to theta upon n, which is our 0.35, and this is 7 divided by 5. So this gives us that our theta prime will be equal to 0.25, or we can write this as 25 by 100, and this comes as 4, which is 1 upon 4. And we are also given that this is our theta prime is our 1 upon alpha, so 1 upon 4, giving us that alpha is equal to 4. So our alpha is equal to 4. Next question. And it states that using Young's double slit experiment, a monochromatic light of wavelength 5000 angstrom produces fringes of fringe width 0.5 millimeter. If another monochromatic light of wavelength 6000 angstrom is used, the separation between the slits is doubled. and the separation between the slits is doubled, then the new fringe width will be. So here, for the second case, we have not only changed the wavelength, but also the slit separation between the slits has been doubled. So you have to keep this in mind. So we have two wavelengths. You can say our lambda 1, that is given to us 5000 angstrom into 10 to the power minus 10 meters. We have our lambda 2, that is over 6000 angstrom 10 to the power minus 10 meters, and initial fringe width, that is our beta 1, that is given to us as 0.5 mm. So this becomes 0.5 into 10 to the power minus 3 meters, and we are also given that the separation is doubled. So we can say initial separation is our D1, then new separation given as D2 will be equal to twice of D1. And we know that our fringe width, that is beta, it is our lambda capital D divided by small d. So for two wavelength, we can write into initial as well as final. We can write that initial fringe width, that is our beta 1, will be equal to lambda 1 d1, and then we have new fringe width, that is our beta 2 will be equal to lambda 2 d divided by d2, and we find out the ratio b2 by b1, beta 1 beta 2 divided by beta 1, and this comes as lambda 2 divided by d2 and lambda 1 d upon d1, and here d and d goes away, and we are left with this will be equal to lambda 2 d1, and we have this as lambda 1 d2, and we already know that d2 is twice of d1, so we substitute it, we get lambda 2 d1 lambda 1 and twice of d1, and this d1 and d1 goes away, so we get beta 2 will be equal to beta 1 multiplied by lambda 2 and twice of lambda 1, and we already know all these values. We substitute it, beta 1 is our 0.5 into 10 to the power minus 3, and lambda 2 is our 6000 10 to the power minus 10, this is twice into lambda 1 is our 5000 minus 10, and we get that our beta 2 will be approximately equal to 0.3 millimeters. So we have 0.3 millimeters, that option number D is the correct one. Option D is correct. Next question, and it states that in a double slit experiment with monochromatic light, fringes are obtained on the screen placed at some distance from the plane of slits. If the screen is moved by 5 into 10 to the power minus 2 meters towards the slit, The change in the fringe width is 3 into 10 to the minus 3 centimeters. If the distance between the slits is 1 millimeter, then the wavelength of the light will be. So in this case, we have to find out the wavelength, and the distance between the screen and the slit is being changed. Let's write the things which are given to us. So first thing that is given to us is our, you can say, small d, that is our distance between the slits is 1 millimeter. So this becomes 1 into 10 to the power minus 3 meters. And we are also given the change in the screen distance, that is delta d. Change in screen distance, which is our delta capital D, and that is given as 5 into 10 to the power minus 2 meters. We are also given the change in the fringe width. Change in fringe width, that is our delta beta. It is also given as 3 into 10 to the power minus 5 meters. And we already know the standard formula, that is the fringe width that is our beta is equal to lambda capital D divided by small d, and from here we can say change in fringe width that is our delta beta will be equal to lambda delta capital D divided by small d, and we need to find out the wavelength. Therefore we can write that our lambda will be equal to delta beta multiplied by small d and divided by change in capital D. So we know all these values. Delta beta is our 3 into 10 to the power minus 5. Small d is given to us 1 into 10 to the power minus 3 meters. Sorry, delta capital D is given, and small d is our 5 into 10 to the power minus 2. And this will be coming as 6 into 10 to the power minus 7 meters. So this is our required wavelength in nanometer. So you can write our lambda will be equal to 600 nanometers. So we get this as 600 nanometers. Next question. We are given in Young's double slit experiment, the fringe width is 12 millimeter. If the entire arrangement is placed in a water of refractive index 4 by 3, then the fringe width becomes in millimeter. So we already know that the relationship between the wavelength with respect to the medium, which is having a certain refractive index, and we also know the we can say relationship between our fringe width as well as the wavelength. So we can just use these two relationships. So first one is that okay, so first is wavelength in a medium, that is our lambda medium will be equal to lambda in a vacuum and divided by refractive index. And we also know that our fringe width that is our beta is equal to lambda capital D upon small d. So therefore from here we can write that our beta in a medium will be equal to beta in vacuum and divided by refractive index, and that beta is given to us a 12 millimeter and refractive index is our 4 by 3. So this comes as 9 millimeter. So option number B is the correct one. B is correct. Next question. And it states that two coherent sources of light interfere. The intensity ratio of two sources is 1:4. For this interference pattern, if the value of I max plus I mean divided by I max minus I mean is equal to 2 alpha plus 1 divided by beta plus 3, then alpha upon beta will be. So we are given two sources and the ratio is 1:4. So we are given that intensity ratio of two sources that is given as I1 is to I2 and is equal to 1:4. And we are also given that I max plus I mean divided by I max minus I mean is equal to 2 alpha plus 1 and beta plus 3. But we know that our I max is equal to square root of I1 plus square root of I2 whole square, and our I mean is equal to square root of I1 minus square root of I2 and its whole square. And we can write this as that I1 is, let us suppose, our I, which gives us that I2 will be equal to 4 times I, common factor. We can say it's K also, K and 4K, and because ultimately they are going to cancel out, so we can write our I max will be equal to square root of I plus square root of 4I whole square, and this comes as our 9I. Similarly, we have I mean, which is square root of I minus square root of 4I whole square, and this will be coming as our I. We substitute the values, we get that I max, that is our 9I plus I, 9I minus I, that will be coming as 10I upon 8I. I and I goes away, and this will be equal to our 5/4, and this 5/4 will be equal to twice alpha plus 1 divided by beta plus 3. And we are going to solve this equation now. It's quite simple. So we get this as 5 beta plus 15 is equal to 8 alpha plus 4. And this can be written as 5 beta plus 11 is equal to 8 alpha, and we can sort it out and we can write this as 8 alpha divided by 5 beta will be equal to 5 beta plus 11 divided by 5 beta, so which can be written 1 plus 11 divided by 5 beta. Therefore, we can say that our alpha upon beta will be equal to 5 beta plus 11, and this comes as a 8 beta, which can be furthermore written as 5 beta plus 15 is equal to 8 alpha plus 4, which gives us that our 8 alpha minus 5 beta is equal to 11. Now we can just compare it, and we have the equation that 5 upon 4 is equal to twice alpha plus 1 and divided by beta plus 3. So we get from here, one second, from here we can write that let 2 alpha plus 1 is equal to 5k and beta plus 3 is equal to 4k. In this way we can easily solve it. So we get this as 2 alpha will be equal to 5k minus 1, and we get beta is equal to 4k minus 3. Therefore, we get multiplying it by 4, we get this as 8 alpha is equal to 20k minus 1, and we get this as 5 beta is equal to 20k minus 15. So if we subtract them, we get this as 8 alpha minus 5 beta will be 11, or we can say our 20k minus 4 minus of 20k minus 15 is equal to 11. So which means that we have k and k goes away, so this equation is true, 11 will be equal to 11. Therefore we can write that 2 alpha plus 1 is equal to 5 and beta plus 3 is equal to 4. This gives us 2 alpha is equal to 4 and beta is equal to 1, giving us that alpha is equal to 2 and beta is equal to 1. We need to find out the ratio, so we can say alpha upon beta is equal to 2 upon 1. So it will be equal to, option number B is the correct one. Option B is correct. Next question. We are given that in Young's double slit experiment, a laser light of 560 nanometer produces an interference pattern with consecutive bright fringes, separation of 7.2 millimeter. Now another light is used to produce an interference pattern with the consecutive bright fringes separation of 8.1 millimeter. The wavelength of the second light is. So here we have, you can say, wavelength that is of lambda 1. So you can say we are given lambda 1, that is our 560 nanometer, and the first separation for fringe width light is given as, let us suppose that is beta 1. So beta 1 is given to as 7.2 millimeter, and we have a beta 2 for the second wavelength, that is our 8.1 millimeter. And we know that our beta, that is a fringe separation, is given as lambda capital D divided by small d. And we have, because here capital D and small d will be constant, therefore we can say that beta is directly proportional to lambda. From here we can write that the ratio beta 1 upon beta 2 will be equal to lambda 1 upon lambda 2. We simply substitute the values, and we get lambda 2 will be equal to, this comes as lambda 1 multiplied by beta 1, beta 2 multiplied by beta 1. Lambda 1 is given to us 560 nanometer, beta 2 is given to us 8.1, and 7.2. So this gives us that our lambda 2 will be coming as 630 nanometers. And this will be 630. Next question, and it states that an unpolarized light beam of intensity 2 I0 is passed through a polarized P and then through another polarized Q, which is oriented in such a way that its passing axis makes an angle of 30 degree relative to that of P. The intensity of the emergent light is. So here we are given that we have two polarities P and Q. So you can say the intensity after passing through polarity P intensity through P, let us call that as our IP, and that will be equal to our I0 divided by 2, and that is our twice I0 is our. So here 2 and 2 goes away, so the IP comes as our I0. And similarly we can say intensity through Q, let us suppose we call that as IQ, which will be equal to IP cos square of theta, and here theta is given to us as 30 degree and IP is our I0. Therefore we can say that our IQ will be equal to our I0, and we have cos square of 30. So this comes as I0 cos of 30 is square root of 3 divided by 2 and its whole square, so which comes as 3 I0 divided by 4. So option number C is the correct one. Option C is correct. Next question. Okay, so these are now advanced questions. We previously which we dealt with were only the, you can say, mains questions. So this is 2022 advance. So first question states that for the advance, a rod of length 2 centimeters makes an angle of 2 pi by 3 radian with the principal axis of thin convex lens. The lens has a focal length of 10 centimeter and is placed at a distance of 40 by 3 centimeter from the object as shown in the figure. the height of the image is 30 square root of 3 divided by 13, and the angle made by it with respect to the principal axis is alpha radian. The value of alpha is pi upon n radian, where n is equal to. So we are given the basic figure. So we have a object which is at a certain angle, and that angle is given with respect to principal axis, and convex lens is placed. Let us call this as lens L, and we get an image which height is given as 30 root 3 divided by 13, and the angle made by this image with respect to the principal axis is given as alpha, and we have said that alpha is pi upon n, so we have to find out the value of n. Basically we are going to find out alpha and then relate it with the pi by n. In this case, let us redraw this figure, and this is your principal axis. So we have a, you can say, object, and this angle is given to us as 2 pi by 3. So we can find out the other angle. This angle will be 60 degree. Okay. And we are given that the length of rod is 2 centimeter. So this rod is given as 2 centimeter. So we can find out the height of the top of this rod with respect to the principal axis, and that will be coming close to as square root of 3. We are given a lens, and its distance from the lens is given as 40 by 3, and we are also given the height of the image and the angle it is making with the principal axis. This angle is given as alpha, and the height is given as 30 square root of 3 divided by 13. Okay. And we can also find out this will be coming as 1, because we know this is angle 60 and this is 90 degree. So we can easily find out using sine and cos. And we are also given that we know the height of the object and we know the height of the image. Okay. So we can use the formula that height of the image divided by height of the object will be equal to our v upon u. Therefore we substitute the height of the image, that is our minus, because it is in the below the principal axis, root 3 divided by 13, and this is root 3 will be equal to v upon, and u is given to us as 40 by 3, which will be coming as negative. And here this root 3 and root 3 goes away, and we can write that our, one second, this is our root 3 and this is our root 3. Okay, this is 13. So we can just sort it out, and we can write that our v will be equal to minus of 30 multiplied by root 3, and this is our 13 multiplied by root 3 multiplied by, we have here 40 by 3. Okay, this comes as minus 40 by 3. And this root 3, and this goes by 10. And we get, this is 43 or 40? This is 40 by 3. Okay, so this comes as 400, minus become plus, so this comes as 400 divided by 13. So let us call this as V1. So we get this distance is our 400 divided by 13. I think, let me check whether it is, I think, okay, we'll sort it out. Let's look 40 by 3. Okay, so we got the V1, and we can use the formula that we have 1 upon V minus 1 upon U is equal to 1 upon F, which gives us that our 1 upon V will be equal to, and we have focal length of 10, and we have our U is our 40 by 3, so this comes at 3 by 40. Okay, and this will be coming LCM as our 40, so this will be our 10, this is 4 minus 3, this comes as 1 upon 40. Therefore we can say that our V will be equal to 40. So we found out V is equal to 40, so it means this distance will be equal to 40. And let us call this distance our x. So we can say our x will be equal to 400 minus 40 minus 400 by 13. We can say our x is equal to 40 minus 400 by 13, and this comes as 400, this is our 13, 0, and this comes as 12, and this comes as 520 minus 400, and this will be equal to our 120 divided by 13. Okay. Now we can easily formulate our tangent of alpha. So you can say tangent of alpha will be equal to, we are given, this is 30 square root 3 divided by 13. So we have this as 30 square root of 3 divided by 13, and we found out our x is equal to 120 divided by 13, and this will be equal to, we can just solve it now. So we comes as 30 square root of 3, and here we have 13 into 120 multiplied by 13, and we have this 13 and 13, 0 and 0, and this comes as 4. Okay. I think there is some problem in the data because alpha pi upon n. So let me recheck whether Ah, sorry, my mistake. This is 40 by 3 and this entire distance will be 40 by 3 plus 1, that is 43 by 3. Yeah, my mistake, sorry. So this will be coming as 43 and this will be also my 43. Okay. Now it comes as 430. And this is okay, and we have to sort it here also. This comes as 430, 430, and this gives us 90. Yes, now hopefully it will be sorted out. So this comes as 90. So we can write this as 30 into square root of 3 divided by 13, and this is about 90 multiplied by 13. Now this 13 and 13 and 0 and 0, this goes by 3. Now it's okay. This is root 3 by 3, and we can write this as 1 upon square root of 3. Therefore, we can say that alpha is equal to 30 degree, which is about pi by 6. And we are given this as about pi upon n is equal to pi upon 6, giving us that value of n is equal to 6. Okay, that was my silly mistake. So we found out our value of n is equal to 6. Next question. In this question, it says that 3 plane mirrors form an equilateral triangle with each side of length capital L. There is a small hole at a distance L greater than 0 from one of the corners as shown in the figure. A ray of light is passed through the hole at an angle theta and can only come out through the same hole. The cross section of the mirror configuration and the ray light lie in the same plane. So we have to find out which of the following is the correct options. So we are given this figure. You can say equilateral triangle. So each angle will be of 60 degree, and this is a hole, and angle ray is incident on it at an angle of theta, and this hole is at a distance of small l from one of the corners. Okay. So in the first case, it says that the ray will come out for theta is equal to 30 degree for the value of L, which we can say value of hole should be between 0 and capital L. Okay. So let's draw the ray diagram for it. So we are given that theta should be 30 degree, and we know we are given that this L should be lying between the 0 and capital L. And for that we can just draw the figure, and we have a hole here, and the angle is given as 30 degree, and if this is our 60, and So we have this angle will be over 30. This angle is also 30 because theta is given as 30 degree, and theta is with respect to the side of the you can say triangle. And if these two are you can say 30, so automatically this will be over 90 degree. Okay, so it means if that is 90 degree, the ray of light will be coming, because it is a mirror, so there will be a reflection which will be passing through the same point, that is when the angle is over 30 degree. So option A is the correct one. You can say option A is correct. A is correct. So all these are mirrors. Okay. In the second case, it states that there is an angle for L is equal to L by 2 in which a ray of light will come out after two reflections. Okay. So we have to find out that whether it will coming out after two reflections. So option B, it says that small l is equal to capital L divided by 2, and we have two reflections. So let's draw the ray diagram again. And it says that there is an angle. Okay, so there is certain angle, and you can say the hole is now at the center, and that is our this is our L by 2, and this will be also our L by 2. And if ray is incident at a certain angle, and it will be striking somewhere here, and this angle is 60 degree, and so this angle will be also 60, and this will be also 60, and accordingly we are going to get this is 60, so this angle will be also 60 degree. Now if we draw a normal at this particular point, then this angle will be about 30 degree, and ray of light will be reflected in this way, because this angle should be also over 30 degree, and automatically this angle will be 60 degree. So you can see our A, we have this is B, and this is our C. So obviously BC will be parallel to our, let us call this as P, Q and R. So you can say BC is parallel to our QR. And so this angle is also 60. So once again we are going to get this angle 60, and if we draw a normal here, so we are going to get this angle as 30, and the ray of light will be traveling somewhere here in this direction, because this angle will be also 30. Okay. So we can say that for angle theta is equal to 60, for theta is equal to 60, ray will be coming out after two reflections. Okay, ray comes out after two reflections. So option B is also correct. Option B is correct. And for C states that the ray will never come out for theta equal to 60 and L is equal to capital L by 3. So we are given that theta is equal to 60 and small l is equal to capital L divided by 3. And once again, we can draw the approximate figure for that. Let me draw a bigger one this time. And we have this as P, Q and R, and we have the hole is at L by 3. So this will be, other side distance will be 2L by 3. And angle is given to as a 60 degree. So this is over 60. Okay. So obviously it is going to strike the opposite end, and this angle will be also 60, and we know this angle is also 60, so we are going to get this angle will be also 60. And we can just draw an approximate normal here. So the entire angle will be 90, so we are going to get this angle as 630. And similarly we can say we are going to have a parallel ray, because this angle will be about 30 and this angle will be 60, so this angle will be also equal to 60. So let us call this as A, this is our B and this is C. So we can say our BC is parallel to QR. BC parallel to QR. And here we can just draw a normal. Something like this. This is C and this angle will be over 30, and ray of light will be traveling somewhere here. So it is in this direction, this and this. Okay. And we are going to get that this angle is our 30, so this will be also 30, and we are going to get this angle below 60. So let us draw a normal here, and it is going to strike on the other hand will be our 2L by 3. So this will be 2L by 3 and this will be L by 3. And from here it is going to bend in this way, and similarly it will be coming parallel, and ultimately it is going to pass through this hole and going back. Okay. So we have this angle of 60, so this will be also 60 and this is 60. So this angle is also 60, and here we are going to have 30 and 30. This will be 30 and this will be 30. So everything will be this way. Okay. So it will be going through. We have 1 at B, 2, and this is our BC. Let us call this a D. We have our E and we have a F. So there are total 5 at B, C 2, D 3, and one second. This is 1, 2, 3, 4, 5. Yeah. So we have total 5 reflections. And he says that it will never come out. So option C is incorrect. It comes out after 5 reflections. And we come to the last part, and it states that if theta is equal to 60 and this our small l lies between L by 2 and 0. So we can say that theta is equal to 60 and our L is, that the position of hole is between L and L by 2, sorry, capital L by 2. And once again we can draw the figure. We can assume any position, and suppose this is our L by 2, and let us assume that we have a position that is our somewhere here, and this position is our L by 4, and angle is given to a 60. So ray of light will be passing through here. This will be 60 and 60, so will be 60, and this will be also 60. So it will be once again going parallel and striking here, going here, once again parallel, and it will be coming out like this. This way. So this is a P, Q, R, and we have this is our A, B, C, D, E, and F. So once again we have 1, 2, 3, 4, and 5. Okay, so we have 5 reflections, and it says after 6 reflections. Option number D is also correct. So only option A and B are the correct one. Options A and B are correct. Next question. And it states that consider a configuration of n identical units, each consisting of 3 layers. The first layer is a column of air of height h, that is 1 by 3 centimeter. The second and the third layer are of equal thickness d, which is given as square root of 3 minus 1 divided by 2, and a refractive index size is mu1 root 3 by 2 and mu2 root 3 respectively. A light source O is placed on the top of the first unit as shown in the figure. A ray of light from O is incident on the second layer of the first unit at an angle of 60 degree to the normal. For a specific value of n, the ray of light emerges from the bottom of the configuration at a distance of L, that is given as 8 square root of 3 centimeter as shown in the figure. The value of n is. So this consists of n units, and each unit consists of air and 2 mediums having refractive index mu1 and mu2. And the height of both the mediums mu1 and mu2, that is d, is same, whereas the A having height of h. And there are total of n units. And it also states that the light emerges from the final unit at a distance of this L. Okay. And it is given as 8 square root of 3 centimeters. So we have to find out what will be the number of units. Okay. So let us state the things which are given. So first thing that is given to us is our height of the air column, that is h is equal to 1 by 3 centimeters, and thickness of the layers is given, that is d. We have square root of 3 minus 1 divided by 2, and we have refractive index of second layer, that is our mu1 is root 3 by 2, and the third layer refractive index is given as root 3, and we are given that the angle of incident is given as 60. It says that the ray of light from O is incident on the second layer of the first unit at an angle of 60 degree. And total horizontal distance is also given, that is our, so you can say horizontal distance that is given as L is given as 8 square root of 3. So here we are going to use Snell's law and respective the tangent, that is sine upon cos theta, that is a normal trigonometric identity. So let us broadly discuss first unit, and then we can replicate it for the other units also. So we can draw the figure for the first unit. And so first we have this as air, and then we have a mu1 refractive index, and then we have mu2 refractive index, and this is repeated n number of times. And we are given that this distance is d, and this is also given as d, and we are also given the height of the air, that is 1.1/3. That means this is given as our h. So ray of light is incident, and this angle is given to us as 60 degree, and it is going to bend somewhere like this, and it is going to further bend something like this. So let me complete these triangles. So let us call this as A, this is B, and this is our C. And we are given h. H is given to us as 1/3. So this angle will be over 30 degree. So we can easily find out that this distance will be equal to over 1 upon square root of 3. So if we use Snell's law at A, let us call this angle as θ1. So we can say Snell's law at A, and this gives us, for air, let us call this as mu3. So we can say mu3, and we have this is sine of 60 is equal to mu1 and sine of θ1. Mu3 is our 1, so we get this as sine of θ1 will be equal to 1 multiplied by sine of 60 and divided by mu1, and sine of 60 is square root of 3 divided by 2, and mu1 is given as square root of 3 divided by 2, and this comes as square root of 2 divided by 2, giving us 1 upon square root of 2. Therefore we get our θ1 is equal to 45. So we get that our θ1 is equal to 45, and d is given to us. Therefore we can say our d is given to us as square root of 3, square root of 3 here. So this square root is only with 3, not with 1. And d is given to us, so we can easily find out now this. D is given to us square root of 3 minus 1 divided by 2. Okay. So θ1 is 45, so this will be also coming as square root of 3 minus 1 divided by 2. So if we have this as 45, so this angle will be also over 45. So now let us call this angle θ2. So we are going to use Snell's law at B. At B. Now if you use Snell's law at B, we can say that mu1 sine of 45 will be equal to mu2 sine of θ2, and we are supposed to find out θ2, so we can write this as sine of θ2 will be equal to, this will be our mu1 upon mu2 sine of 45. Mu1 upon is, mu1 is given to us square root of 3 divided by 2, mu2 is given to us square root of 3, and we have sine of 45 1 upon 2 square root. So this comes as 1.2. Therefore our theta 2 will be equal to 30 degree. So we found out our theta 2 is our 30, and this d is same. So once again we can find out this distance, and that will be coming equal to as root 3 minus 1 and divided by 2 root 3. And we are also given that the horizontal displacement which we found out, let me call this as this, let us call this as d1, this distance as d2, and this distance as d3. Okay. So we can say horizontal distance that is our, for first is our air layer, that is our d1, which will be coming a h tangent of 30, giving us 1 by 3 root 3. So this comes as 1 upon root 3. Next is for second layer, that is our d2. This will be d tangent of 45, and d is our square root of 3 minus 1 divided by 2 multiplied by 1. So this comes as square root of 3 minus 1 divided by 2. And finally is our third layer. Third layer is our d3. So this comes as d, and the angle is our 30. And this comes as square root of 3 minus 1 divided by 2, and this comes as 1 upon square root of 3. This comes as square root of 3 minus 1, and this is 2 root 3. One second, I think I made a mistake here. One second. Oh, yes. 60. I mean. No, it's okay. Some, I think, if I am reading correctly, is incident on the second layer of the first unit at an angle of 60. Is it correct? Let me check whether this statement is correct or not, because it states that second layer yes, so this will be 60. Yeah, now it's correct. Yeah, I was confused. Think, let me recheck it again. Yeah, now it's okay. So we found out our D1, D2 and D3. So we can say our D total displacement in 1 unit in 1 unit, let us call this D total, will be equal to D1 plus D2 plus D3, and this gives us square root of 3 divided by 3 plus square root of 3 minus 1 divided by 2 and plus square root of 3 minus 1 divided by 2 root 3, and this we can write will be equal to 2 root 3 divided by 3, and there are total of n units, and their n unit will be equal to displacement because of 1 unit, that is d total, multiplied by n will be equal to total length, that is our L. You can say that for n units, we can write n multiplied by d total will be equal to our L. So we get our n is equal to L divided by d total, and this L is given as 8 square root of 3 divided by 2 square root of 3 divided by 3, and is 8 root 3. So from here get our n will be equal to 8 divided by square root of 3 multiplied by this comes as 3 divided by 2 root 3, and this 3 goes away, this goes by 4, so we have n is equal to 4. So value of n is equal to 4. Next question. And it states that an object and a concave mirror of focal length f 10 cm Both move along the principal axis of the mirror with a constant speeds. The object moves with a speed v0, 15 cm per second, towards the mirror with respect to a laboratory frame. The distance between the object and the mirror at a given moment is denoted by u. When u is equal to 30 cm, the speed of the mirror Vm is such that the image is instantaneously at rest with respect to the laboratory frame, and the object forms a real image. The magnitude of Vm in centimeter per second is. So we are given this figure. So we have a mirror Vm moving with velocity Vm and an object moving with velocity V0, and at particular time the distance between the mirror and the object is given as u. So we can write the given information, and we are given the focal length, that is our f is 10 centimeter, and we are given velocity of the object v0 is our 15 centimeter per second, and we are given the distance between the object and the mirror at any particular time is u is our 13 centimeter. So here we are going to use, you can say, basic formula, that is mirror formula, and we can write that 1 upon f is equal to 1 upon u plus 1 upon v. And if we differentiate this equation, we are going to get, because focal length will be our constant, so we can write from here that dv by dt will be equal to minus, this comes as u upon v upon u whole square and du by dt. Okay. And if we you can say measure the velocity of the image as well as object with respect to lab frame, okay, that will be much more convenient, because everything is with the velocities are given, or the explanation is with respect to the laboratory frame. So we can say that velocity of image with respect to lab frame, let us suppose that is given as v of I. So we can say vi will be equal to v prime plus velocity of the mirror, that is vm, and here v prime is velocity of image with respect to mirror. And similarly we can write that velocity of object with respect to lab frame, and we can write this as v0 with respect to lab frame will be equal to v0 plus vm, and v0 we already know, it is given to us, which is our velocity of object with respect to mirror. Velocity of object with respect to mirror, this is given to us. Now we are going to use all these explanation of formulas and find out the required things. Okay. So first of all we are going to use the mirror formula. So we have 1 upon f is equal to 1 upon u plus 1 upon v. From here we are going to find out our v. So focal length is given as 10, object is given as 30 at a particular time. So from here we get our v will be equal to 15 centimeters. And now we are going to use the velocity part of the equation. So we know that dv by dt is equal to minus v upon u whole square and du by dt. and this dv by dt is nothing but our v prime. So we get our v prime is equal to, let me write it as capital V. V prime V prime. So I get my V prime will be equal to, this is minus, and we just found out 15, 30 whole square, and this velocity is given to us as minus of 15. Okay, and here this is our du by dt is nothing but v naught, and v naught is moving towards the mirror, so that's why taken as a negative. So we get our v prime will be equal to 15 by 4 centimeter per second. Next, we are going to find out the velocity of the mirror. And you can say velocity of the image with respect to lab frame. Velocity of image with respect to lab frame is equal to 0. Therefore, we can write that Vi, which is equal to over V prime plus Vm, will be equal to 0, and we substitute value of V prime, which we just found out. From here we get our Vm will be equal to minus 15 upon 5, sorry, it is 15 upon 4, let me check. This goes by 2, this is 15 by 4, okay, so this will be 15 by 4. And we have this 15 by 4 centimeter per second. Use 30, the speed of this such that the image is still doesn't look good. 1 second. This is okay. 15, and let me check. I think I missed something. V naught is 15. Yeah. 1 second. Yeah, this is. So we found out that our v prime and 15/4, and this is okay, 15/4. Okay, so we can write that our velocity of mirror minus 0 will be equal to, this is our 15/4, and this we have our Vm minus of V naught. I think this looks, 1 second, let me correct it from here. Okay, so we have this by dv by dt, and we can write this as our velocity of mirror minus 0 will be equal to minus, and we have 15/30 whole square, and the relative velocity is our Vm minus of V naught. And now it's okay. So we come this as Vm is equal to, this will be minus and 5/2, so this becomes 1/4. This is a Vm minus our V naught, and V naught is our 15. So this comes as 4 times Vm minus of Vm, and this is minus of 15. Therefore, this is a minus of 4 minus this, and this becomes plus. Now this becomes V plus and 15, giving us Vm is equal to 3 centimeter per second. Now it's the correct one. Okay, I messed it up. Okay, next question. And it states that a double slit setup is shown in the figure. One of the slits is in medium 2 of refractive index N2. The other slit is at the interference of this medium with another medium 1 of refractive index N1, which is not equal to N2. The line joining the slits is perpendicular to the interface, and the distance between the slit is d. The slit widths are much smaller than d. A monochromatic parallel beam of light is incident on the slits from a medium 1. A detector is placed in medium 2 at a large distance from the slits and at an angle of theta equals to the angle of refraction of the beam. Consider two approximately parallel rays from the slits received by the detector. So based on this, we have total of 4 options here, and we are going to find out which of them will be the correct one. So we have two medium N1 and N2, and detector is placed in the medium 2, and the slit are there 2 slits, and it states that we have to consider approximately 2 parallel rays from the slits that are being received by the detector. So let us draw an approximate figure, and let us suppose this is our medium interface, and we have N1 and this is N2, 2 parallel rays. So let us put this is first ray, and we have this as second ray, normal, and here also normal. We have this as A, let us put this as our B, and so this is going to bend in this way as well as this is going to bend in this way. And so let us draw perpendiculars from A. Let us call this as A, this is C, and perpendicular from B to here, let us call this as D. And if we say our this angle is of alpha, and we can write this angle will be also over alpha, and if this angle is of theta, so this angle will be also theta. Okay. This is 90 degree and this is also 90 degree, and the slit width is given as to us D. So we have D, and this is entirely in medium 2. Okay, so this is our D, and this angle will be also over theta. So this is A, B, C, D, and this angle will be also over theta. So we got all the angles. So we can write that our tangent of theta, let us call this is A, B, C, D, and let us call this as point as E. So if we can say that tangent of theta will be equal to AB divided by D, AB, and this gives us that of AB will be equal to D tangent of theta. Okay. And similarly, we can write that our sine of alpha will be equal to BC upon AB, and from here we can say our BC will be equal to AB, and we have this is sine of alpha, and AB is our D tan of alpha, so we can write that our BC will be equal to D tangent of theta multiplied by sine of alpha. Similarly, we can write that our sine of theta will be equal to, we have this as AD divided by AB. AD divided by AB. Now the path difference. From here we can say that our AD will be equal to our AB, and we have this as sine of theta. So we can say our path difference that is our delta of x is equal to, we have refractive index n1 BC minus refractive index n2 and AD, and if we substitute value of BC and AD, we can write that our delta of x will be equal to n1, and we have this as AB sine of alpha minus n2, and this AB sine of theta, and AB we can take as common, so this comes as AB, and we have this as n1 sine of alpha minus n2 sine of theta. And according to Snell's law, you can say Snell's law, it gives us that our n1 sine of alpha is equal to n2 sine of theta. Therefore, we can write our delta of x will be equal to AB, and we can easily substitute it now, n1 sine of alpha minus n1 sine of alpha. These two cancels out, so this phase delta of x will be equal to 0. And from here we can find out the phase difference. We can say that phase difference that is our delta of phi, which is given as 2 pi upon lambda, and delta of x. Delta of x is 0, so we get phase difference that is delta of phi will be equal to 0. So we can say that our phase difference is independent of d. Option number A is correct. And the two rays interfere constructively as a detector because the phase difference is 0. So there will be having a constructive interference. So this means constructive interference. So option number A and B are correct. So I think this completes all the questions. Yes, so these were the 19 questions which were asked in the 2022 mains as well as advanced. So this was the only part 1. For the rest of the remaining questions, we are going to conclude them in part 2. Thank you.